Good evening, and welcome to The Sleepy Scientist. It's wonderful to have you here. Tonight we'll be looking at something that stretches across billions of stars, billions of years, and an unimaginable amount of empty space, and yet arrives at a question that is unsettlingly simple. Why is the universe so quiet? Just a little favour to ask before we begin. If you have a moment to spare, I'd really appreciate it if you took a look at our ebook over on the Sleepy Scientist website. It takes the ideas from these videos and gives them room on the page, unhurried, laid out with all the space they need to properly settle in the mind. The whole thing is narrated too, so you can read it or simply listen, and at the close of each movement there's a short quiz waiting, a gentle way to see what's stayed with you, and to turn the ideas over once more before moving on. The QR code is up on screen, and there's a link in the description to thesleepyscientist.com whenever you're ready. Every reader who takes a look is the reason these videos keep appearing, and to anyone who takes the time to buy it, I don't think you quite understand how much that means. That's the only ask tonight, and thank you sincerely. Now, I'd love to know where in the world you're watching from tonight. Perhaps you're listening from a quiet bedroom, curled up on the sofa, travelling somewhere in the dark, or settling down after a long day. Wherever you are, I hope you're comfortable, relaxed, and ready to let your thoughts wander for a while. And if you enjoy these calm journeys through science, a like and a subscribe are always appreciated. The Milky Way holds billions of stars, many of them far older than the Sun. Planets appear to be common, and some worlds may have had billions of years longer than Earth to produce life and perhaps technology. So if anyone else is out there, where is everybody? This is the Fermi Paradox, and tonight we'll explore the Drake equation, the Great Filter, the rare earth hypothesis, the dark forest, and the possibility that alien intelligence may simply be too distant, too quiet, or too unfamiliar for us to recognise. I'll do my best not to make the silence of the cosmos sound too dramatic, though the universe does seem determined to keep its secrets. So get comfortable, let the noise of the day begin to fade, and let's start with the question that has been waiting in the dark for rather a long time. If the galaxy has had all the time in the world, why has nobody called? On a clear night, far from the glow of streetlights and windows, the sky can seem almost crowded. Stars appear in every direction, some bright and steady, others faint enough to disappear when you look directly at them. Yet even the richest night sky offers only the smallest glimpse of what is actually there. Every star visible to the unaided eye belongs to the Milky Way, but nearly all of the galaxy remains hidden from view. Dust blocks some of its light. Distance makes most stars too faint to see. Even under perfect conditions, the human eye can detect only a few thousand stars at once. The Milky Way contains roughly 100 billion stars, although estimates vary because counting every star in the galaxy is not quite as convenient as counting chairs in a quiet room. Many of those stars are accompanied by planets. Some have one or two. Others belong to systems containing several worlds, along with moons, asteroids, comets, rings, and clouds of smaller debris. Modern astronomy has shown that planets are not rare exceptions. They are ordinary products of star formation. Before the 1990s, scientists had confirmed no planets orbiting ordinary stars beyond the Sun. Today, thousands of exoplanets have been identified, and statistical studies suggest that the Milky Way contains at least tens of billions of rocky worlds. Many more planets will remain undetected because they are too small, too distant, or positioned in ways that make them difficult for our instruments to observe. Some of those worlds orbit within the habitable zones of their stars, where temperatures might allow liquid water to exist on the surface under suitable atmospheric conditions. This does not mean they are inhabited. A planet can orbit at the right distance and still be dry, frozen, airless, poisonous, or otherwise thoroughly unwelcoming. Even so, the numbers are difficult to ignore. The galaxy appears to contain an immense collection of possible environments in which life might arise. It has also existed for billions of years longer than human civilization. Many stars and planets formed before the Sun, leaving enormous amounts of time for biology, intelligence, and technology to develop elsewhere. And yet humanity has found no confirmed evidence of another technological civilization. No verified message has arrived from a distant star. No artificial spacecraft has been discovered moving through the solar system. No alien artifact has been recovered from the Moon, Mars, or any asteroid. Astronomers have not identified a megastructure surrounding another star, nor any other technosignature that can be confidently attributed to extraterrestrial engineering. There have been strange signals, unusual stars, unexplained observations, and moments of genuine excitement. So far, however, every promising case has either received a natural explanation, been traced to human interference, or remained too uncertain to support an extraordinary conclusion. This absence is sometimes called the Great Silence. The phrase does not mean that the universe is literally silent. Space is filled with radio waves, magnetic activity, stellar explosions, colliding objects, and radiation left behind by the early universe. The silence refers specifically to the lack of convincing evidence for extraterrestrial technology. It is also important to recognize what that silence does not tell us. It does not prove that Earth is the only inhabited world. It does not prove that intelligence has never appeared elsewhere. It does not prove that no civilization is currently transmitting. It tells us only that our searches have not yet produced a confirmed detection. This distinction sits at the heart of the Fermi Paradox. Despite its name, the Fermi Paradox is not a formal contradiction in the mathematical sense. It is a tension between two ideas that both appear reasonable. The first is that the Milky Way is extremely large, extremely old, and filled with planets. The second is that we see no unmistakable evidence of anyone else. If technological civilizations are common, long-lived, and interested in spreading through space, the galaxy might be expected to contain visible signs of their existence. The fact that it does not appear to contain those signs demands an explanation. Part of the difficulty comes from the way several very different questions are often grouped together. Simple microbial life is not the same as complex life. Complex multicellular organisms are not necessarily intelligent. Intelligence does not automatically produce science or engineering. A species capable of technology may never develop radio communication or interstellar travel, and even a civilization with advanced machines may remain detectable for only a short period. Earth itself demonstrates these differences. Life has existed here for billions of years, but technological civilization appeared only very recently. For most of Earth's history, an observer on another world would have found a living planet with no radio transmitters, no artificial satellites, and no signs of industry. The silence could therefore have many explanations. Perhaps life rarely begins. Perhaps simple life is common, but complex cells are unusual. Intelligence may be a rare evolutionary accident. Technological societies may destroy themselves, become quiet, or lose interest in the outside universe. Some may deliberately hide. Others may communicate in ways we cannot detect. Interstellar expansion might be too difficult, too expensive, or simply too unappealing. Our searches may have covered far less of the galaxy than they sometimes appear to have done. Humanity may also have arrived unusually early, before most technological civilizations have had time to appear. Each possibility carries different assumptions. Some are supported by familiar biology or physics. Others depend heavily on speculation about minds and societies that may be nothing like our own. For now, the night sky offers no final answer. It simply presents an extraordinary contrast. A galaxy filled with stars, planets, chemistry, energy, and time appears to contain no obvious neighbours. Whether that silence reflects emptiness, distance, rarity, caution, bad timing, or the limitations of our search remains one of the most quietly persistent questions in modern science. The silence of the Milky Way becomes more puzzling when its age is placed beside its size. Our galaxy stretches roughly 100,000 light-years from one side to the other. Light itself, moving at the fastest speed allowed by known physics, requires about 100,000 years to cross that distance. For a human lifetime, this is almost impossible to picture. For the galaxy, however, it is a relatively brief interval. The oldest known stars in the Milky Way formed more than 13 billion years ago. Many belong to ancient populations created when the galaxy was still assembling from smaller clouds and early stellar systems. The Milky Way has therefore been producing stars, planets, and complex chemistry for nearly the entire history of the universe. The solar system is much younger. The Sun and its planets formed approximately 4.5 billion years ago, meaning that some planetary systems had already existed for billions of years before Earth appeared. Even if the first generations of stars lacked enough heavy elements to form rocky planets easily, later generations would have contained carbon, oxygen, silicon, iron, and the other ingredients needed to build solid worlds. Some planets could therefore have developed stable environments, life, intelligence, and technology long before the first animals moved through Earth's oceans. That does not mean such civilizations definitely existed. It means that time was available. Interstellar travel is slow, but it does not need to be particularly fast to become important over galactic history. A spacecraft travelling at 1% of the speed of light would still be far beyond anything humans have constructed, but it would cross the distance to a nearby star in a few centuries rather than millions of years. Crossing the entire Milky Way in one uninterrupted journey would take roughly 10 million years at that speed. A real expansion would almost certainly take longer because spacecraft would stop, systems would develop, and new expeditions would need to be prepared. Yet even a journey lasting tens or hundreds of millions of years would occupy only a small fraction of the galaxy's age. More importantly, expansion would not have to proceed as one ship travelling from one edge of the Milky Way to the other. It could unfold as a branching process. A civilization might first travel to one nearby star. After settling there, building equipment, or establishing an automated base, that new system could eventually send expeditions toward several more stars. Each of those destinations could then repeat the process. The individual journeys would remain local. Most might cover only a few light years, but the combined pattern would gradually spread outward, rather like seeds moving from one patch of ground to the next. The expansion would begin slowly. After enough settled systems existed, however, the number of possible launching points would increase. A civilization would not need to organize every expedition from its original home planet. The process could continue through independent communities, scientific organizations, machines, or descendants whose goals differed from those of the society that first began the journey. This reasoning became central to influential arguments developed by astronomer Michael Hart and physicist Frank Tipler. Michael Hart argued that if technological civilizations commonly arose and expanded between stars, one should already have reached the solar system. Frank Tipler later suggested that advanced societies could explore the galaxy using self-replicating robotic spacecraft. These hypothetical machines are often described as von Neumann probes, named after mathematician John von Neumann. Von Neumann studied the general logic of self-reproducing machines, although he did not design an interstellar probe fleet. A self-replicating spacecraft would travel to another planetary system, collect local materials, manufacture copies of itself, and send those copies onward. In principle, this could reduce the need to launch every machine from one homeworld. No fully autonomous interstellar machine of this kind currently exists. Even on Earth, building a machine capable of locating raw materials, refining them, constructing complex electronics, repairing itself, and reproducing without human support remains far beyond present engineering. The idea is nevertheless useful because it demonstrates that galactic exploration may not require biological travellers to survive every journey. Machines can potentially tolerate long periods of inactivity, harsh radiation, and very slow travel more easily than living crews. Modern computer models have examined these ideas without assuming impossibly fast spacecraft or perfectly organised expansion. Jonathan Carroll Nellenbach, Adam Frank, Jason Wright, and Caleb Scharf modelled the movement of civilizations through a changing galaxy in which stars orbit, pass near one another, and gradually create new opportunities for travel. Their simulations showed that a civilization could spread widely through the Milky Way, even when spacecraft moved slowly, and long pauses occurred between launches. The motion of stars themselves helps by bringing systems closer together over time. The results also revealed an important complication. A galaxy can become extensively settled without every star being visited. Some systems may remain isolated because of distance, timing, unsuitable conditions, or simple chance. Earth could therefore remain untouched even if settlement had occurred elsewhere. Galactic expansion also does not have to resemble a single empire covering a map. It could consist of independent settlements that lose contact with one another. Scientific probes might travel without carrying colonists. Machines could map planets and then move on. Civilizations might send libraries, artificial minds, genetic material, or dormant microorganisms rather than living populations. Some forms of expansion might be almost invisible. A small probe drifting through a planetary system would be considerably harder to detect than an enormous fleet arriving with dramatic lighting and an unnecessarily confident soundtrack. The strongest version of the argument therefore rests on a hidden assumption. At least one technological civilization must survive for long enough, retain the ability to travel, and continue choosing to spread. It must avoid permanent collapse, loss of interest, or technological retreat. Its descendants or machines must preserve some version of that outward movement across immense periods of time. If no civilization meets those conditions, the age of the galaxy may not matter, but if even one did, the Milky Way appears to have offered more than enough time for its presence to become difficult to miss. The famous question at the centre of this puzzle did not begin in an observatory, a lecture hall, or a published scientific paper. It began over lunch. In the summer of 1950, physicist Enrico Fermi was working at the Los Alamos Scientific Laboratory in New Mexico. He was already one of the most respected scientists of his generation, known for his work in nuclear physics, particle physics, and quantum theory. One day, Fermi went to lunch with three colleagues: physicist Emil Konopinski, physicist Edward Teller, and physicist Herbert York. Their conversation wandered through several subjects, as lunchtime conversations often do. Recent newspaper stories had been discussing flying saucers, following a wave of public interest in unidentified objects in the sky. A humorous cartoon had also appeared, joking that aliens might be stealing rubbish bins from the streets of New York. From there, the group began discussing whether travel between the stars was physically possible. They considered the enormous distances involved, the speed spacecraft might reach, and the length of time required for a civilization to spread from one planetary system to another. The conversation was partly serious and partly playful, but it touched on a genuine scientific issue. If technological civilizations existed elsewhere, and if some of them were much older than humanity, then at least a few might have had enough time to explore a large portion of the Milky Way. The discussion moved on to other things. Then, during lunch, Enrico Fermi suddenly asked a remarkably simple question. Where is everybody? The exact wording is not completely certain. Different people remembered the conversation in slightly different ways. Fermi may have asked where the aliens were, where the visitors were, or why there was no obvious evidence of them. Whatever the precise sentence, the meaning was clear. If the galaxy was old, if stars and planets were numerous, and if interstellar travel was possible even at modest speeds, why had no one appeared? Why were there no visitors, no spacecraft, no machines, and no unmistakable signs that another civilization had reached the solar system? It was a small question carrying an enormous amount of reasoning inside it. Fermi was famous for making quick estimates from limited information. These became known as Fermi problems. He would break a large question into smaller pieces, make sensible approximations, and arrive at an answer that was not exact, but was often surprisingly useful. He may have applied the same instinct to extraterrestrial civilization. The Milky Way was billions of years old. The distance between neighbouring stars, although immense by human standards, was not impossible to cross over long periods. A civilization capable of sending expeditions to nearby systems could gradually establish new launching points. Over enough time, the process might spread across the galaxy. If those assumptions were correct, then the absence of visitors seemed difficult to explain. The modern phrase Fermi Paradox can make it sound as though Fermi presented a complete scientific theory at lunch. He did not. He never published a formal argument called the Fermi Paradox. He did not leave behind a detailed list of assumptions or a mathematical demonstration showing that alien civilizations must exist. Much of what is known about the conversation comes from recollections collected decades later. In the 1980s, physicist Eric Jones contacted Emil Konopinski, Edward Teller, and Herbert York and asked them to describe what they remembered. Their accounts agreed on the broad shape of the discussion but differed in some details. Later historians and scholars have therefore treated the story carefully. Fermi's original concern may have been narrower than the modern paradox. He may have been asking why Earth had not been visited if interstellar travel and expansion were common. He may not have been asking why astronomers had failed to detect radio messages, engineered stars, or distant technological activity. Those broader questions developed later. In the 1975, astronomer Michael Hart argued that the absence of extraterrestrial visitors provided strong evidence that no advanced civilization had spread through the Milky Way before humanity appeared. A few years later, physicist Frank Tipler developed a related argument involving self-replicating robotic probes. Tipler suggested that even a single technological civilization could eventually explore or influence the galaxy using machines capable of producing new copies of themselves. Radio engineer David Viewing had also published an earlier discussion of interstellar settlement and the absence of extraterrestrial visitors. Together, these arguments helped transform Fermi's lunchtime remark into the modern version of the paradox. The question was no longer only why aliens had not landed on Earth. It became a much wider problem. If advanced civilizations exist, why have we detected no confirmed radio transmissions from them? Why have astronomers found no artificial laser signals aimed across interstellar space? Why do distant stars show no verified evidence of enormous engineered structures collecting their energy? Why have telescopes detected no atmospheric chemicals that can be confidently identified as the products of alien industry? Why have we found no probes, abandoned machines, altered planets, artificial heat sources, or other clear signs of large-scale technology? This wider absence is what is usually meant by the Great Silence. The difference matters because a civilization could exist without ever visiting Earth. It might remain within its own planetary system. It might communicate rather than travel. It might send machines instead of biological explorers. It could alter its star, produce unusual waste heat, or leave chemical traces in a planetary atmosphere. The modern search therefore looks for much more than arriving spacecraft. It looks for techno-signatures, meaning observable evidence created by technology. The uncertain history of the lunchtime conversation does not weaken the scientific question. It simply reminds us that famous ideas are often shaped gradually. Fermi provided the memorable spark. Later scientists expanded the reasoning, challenged its assumptions, and turned it into a broader investigation of life, intelligence, technology, and time. The underlying tension remains. The galaxy offers vast numbers of stars, planets, and ancient opportunities. Our observations have revealed no confirmed technological neighbours. Fermi expressed that tension as an instinctive question. The next step was to make it more systematic by asking not only where everybody was, but how many detectable civilizations should reasonably be expected to exist. The question of how many technological civilizations might exist cannot be answered simply by looking at the number of stars. A galaxy may contain an enormous number of planets, but several uncertain steps separate an ordinary world from one capable of sending a detectable signal. Astronomer Frank Drake developed a way of arranging those steps so that each could be considered separately. Before the equation came the search. In 1960, Frank Drake worked at the National Radio Astronomy Observatory in Greenbank, West Virginia. There, he used an 85-foot radio telescope to listen toward two nearby stars, Tau Ceti and Epsilon Eridani. The experiment was called Project Ozma, named after the distant land of Oz in the children's books by Lyman Frank Baum. Both stars were relatively close to Earth and broadly similar to the Sun. At the time, no planets had been discovered around either of them, but they appeared to be reasonable places to begin listening. Drake tuned the telescope near a frequency associated with neutral hydrogen, the most abundant element in the universe. The reasoning was that another technological civilization studying nature might also recognize this frequency as an obvious place to transmit. Project Ozma detected no confirmed extraterrestrial message. It did, however, demonstrate that a systematic scientific search was possible. Instead of waiting for an alien signal to arrive by chance, astronomers could choose targets, examine specific frequencies, and investigate anything unusual. The following year, in 1961, a small meeting was organised at Greenbank to discuss the search for extraterrestrial intelligence. The participants included astronomer Carl Sagan, physicist Philip Morrison, and Giuseppe Cocconi, geneticist Joshua Lederberg, chemist Melvin Calvin, radio engineer Barney Oliver, organiser Peter Pearman, and several other researchers from different scientific backgrounds. The meeting needed a clear agenda. Frank Drake therefore wrote down a sequence of factors describing the conditions that would determine how many detectable civilizations might exist in the Milky Way at any one time. That sequence became known as the Drake equation. Spoken entirely in words, it says, the number of detectable civilizations equals the rate at which suitable stars form, multiplied by the fraction with planets, multiplied by the number of potentially habitable worlds per system, multiplied by the fraction where life begins, multiplied by the fraction where intelligence develops, multiplied by the fraction producing detectable technology, multiplied by the average length of time that technology remains detectable. The first term concerns stars. New stars continue to form in the Milky Way from large clouds of gas and dust. The relevant question is how many suitable stars form during a given period. Not every star offers the same conditions. Some are extremely massive and live only briefly. Others produce intense radiation or powerful flares. Long-lived, comparatively stable stars may offer better opportunities for life to develop over billions of years. The second factor asks what fraction of those stars possess planets. When Drake created the equation, astronomers did not know whether planetary systems were common. Today, thousands of exoplanets have been confirmed, and observations suggest that planets are ordinary companions to stars. This has reduced one of the equation's original uncertainties, although it has not answered the more difficult biological questions. The third factor asks how many potentially habitable worlds exist in an average planetary system. A world may orbit within the habitable zone, where temperatures could permit liquid water, while still being unsuitable for life. Its atmosphere may be too thin, too thick, or chemically hostile. It may lack water, suffer extreme stellar radiation, or experience an unstable climate. Moons could also offer habitable environments, particularly if they contain subsurface oceans warmed by tidal forces. The next factor asks what fraction of suitable worlds actually develop life. This is one of the greatest unknowns. Life appeared on Earth relatively early in the planet's history, once stable conditions existed. That might suggest that life begins readily when chemistry and environment permit it. It could also mean that Earth was unusually fortunate. With only one confirmed living world, it is impossible to know which interpretation is correct. The following fact asks how often life develops intelligence. Evolution does not move toward a predetermined goal. For most of Earth's history, life consisted entirely of micro